I want to tell you about an experiment you'll be doing in the physical chemistry laboratory. This experiment has to do with polymers. Polymers are substances used in many industries, as I'm sure you're aware, the plastics industry, the clothing industry, throughout biochemistry. And so in this experiment, we're going to characterize properties of a particular polymer. The title of the experiment is The Chain Length and Frequency of Reverse Linkages in a Polyvinyl Alcohol Polymer. And in this section of the video, I'm going to tell you about the theory and calculations. So here you see a picture of a portion of a polymer chain. You can see it's a carbon chain, and there are hydroxy side groups. The chain is composed of monomers, and any sample of polyvinyl alcohol will have chains that can be either of the same length or a variety of lengths. If they're the same length, it's called a monodispersed sample, but more commonly there'll be a range of chain lengths. We call that a polydispersed sample. And what we want to determine for our samples, which are polydispersed, first of all, is the average molecular weight. From the ratio of that to the molecular weight of a monomer, you can determine the average number of monomers in a chain. So that's the first thing we'll determine. Now, the second thing we want to determine is a chemical property displayed sort of right here. So it so happens that when the monomers polymerize to form polyvinyl alcohol, usually they add all in the same direction. So we would say head to tail, head to tail, head to tail. However, occasionally one monomer may add in a reversed fashion. So we'll speak of a reverse linkage. When that happens, you will end up with a moiety here that is a vicinal diol, or a glycol, we say. And the chemical and physical properties of the polyvinyl alcohol may be dependent on the percentage of reverse linkages. So we want to characterize that. We can do so by oxidative cleavage. So we'll treat the sample with potassium periodate. When we do, cleavage occurs at the glycol linkage, and we'll have a sample then that has a smaller reduced mass, hence of course a smaller average number of monomers per polymer. Okay, so in summary then, the major data that we're going to determine from a sample is the average molecular weight and the percent reverse linkages. Now let's talk about the apparatus. The apparatus is a piece of glassware. It's fairly expensive, called an Ostwald viscometer. It's a bent glass tube shaped in this odd way. Notice right here these two marks. One here, one here. These are called fiducial marks. There's an upper one and a lower one. Into the viscometer, you'll put a sample of your polymer dissolved in a solvent, in this case water. You'll be running multiple trials, so you'll need to use the same volume of sample each time. What you will do is via suction, draw up a portion of your sample until the meniscus is above the upper fiducial mark. You'll then remove the suction, and you'll monitor the time it takes the meniscus to pass between the upper and the lower fiducial marks. You'll make a record of that. It turns out that timing will tell us about the average molecular weight. You see, the time it takes for this passage will depend on how thick the sample is. We call the thickness the viscosity. Honey is very viscous, water is less viscous. And the molecular weight will depend on the viscosity. So let's talk about the calculations and how we get to the average molecular weight from the data. So first, we will define with this eta a viscosity coefficient, which is this product, where rho is the density, B is an apparatus constant, implicitly depending on the temperature, and T is the time. Now, the viscosity coefficient depends on concentration and also on temperature, and we need a quantity that is independent of these things. So we will get there in steps. And first, we define a new quantity called the specific viscosity, that's this eta subscript SP, as a ratio -1. And the ratio is of the viscosity coefficient of the solution to the viscosity coefficient of pure solvent, in this case, water. Now you can see that several things will cancel in the ratio. The density and the apparatus constant will cancel, and you'll be left with this ratio simply of times. Incidentally, you'll notice that we're assuming that the density is the same for all solutions and for pure solvent. This won't be strictly true, but it's certainly good enough for our measurements and calculations. We're not there yet, though. So next we need to define another quantity. We call this the intrinsic viscosity. That's this eta in square brackets. And that's defined as the ratio, as concentration approaches 0, of the specific viscosity to concentration, where the concentration is in grams per 100 milliliters. That effectively gives us a quantity that is independent of concentration. So scientists have made solutions of several different known samples of polymer with different average molecular weights, measured the intrinsic viscosity of each, and determined that this equation fits all of the data. So you can use this equation, that particular coefficient, that particular exponent, from your intrinsic viscosities. This will give you the average molecular weight in grams per mole. What about the data? Let's talk about the data you'll take. I suggest recording temperature versus time at roughly 10-minute intervals, simply so that you have a record and you know that your temperature is constant. So then after that, the first trials you'll do will be of pure water. From that, you can get the apparatus constant B. Then you'll do trials for a set of 4 solutions. And I suggest 2 trials per solution, which you'll average. So you'll have solutions of the uncleaved polymer at 2 different concentrations. And you'll have solutions of the cleaved polymer also at 2 different concentrations. So 4 solutions, 2 trials of each. You'll then average the time for each pair of trials. And from the average, you can determine the viscosity coefficient and the specific viscosity. How will you plot your data and get the intrinsic viscosity? Simply this way. So you'll plot the ratio of specific viscosity to concentration as a function of concentration. First for the uncleaved, 2 data points, extrapolate to 0. That gives you the intrinsic viscosity for the uncleaved. Then likewise for the cleaved. Those then are the data that you need for all the things that you need to determine. A few things to watch out for as you perform the experiment. As always, the quality of your results depends on your experimental techniques. So do be careful that the temperature is constant, that when you create the solutions, your dissolution is complete and your transfers are complete from glassware to glassware. You'll need to be sure that there are no particles, undissolved particles of polymer, because if there are, they can become lodged in the viscometer in that small bore. And if that happens, then your timings will be inconsistent. And lastly, you'll want to be sure that your viscometer is always set up so that it's at the same angle, because the time it takes your solution to pass between those 2 fiducial marks will be dependent on the angle of the bore. So it needs to always be at the same angle. So that concludes the theoretical introduction to this experiment. So I want to tell you now about the process of carrying out this experiment, the viscosity and molecular weight of polyvinyl alcohol,
You may have already seen the theoretical calculations intro, but just to frame what we're doing, so we want to characterize a polymer. In this case, it's polyvinyl alcohol, and this is important because polymer chemistry is a major thing, important for industry, and characterizing polymers is an important thing for their properties, especially their physical properties. So we're going to do this. So we've got one particular polymer. It's polyvinyl alcohol. We have a sample here, but we do not know the average molecular weight of this sample. And so we're going to carry out an experiment that will tell us the average molecular weight. That will be our first goal. The properties of the polyvinyl alcohol will be sensitive to the average molecular weight. Secondly, as you'll hear elsewhere or read about, the monomers of polyvinyl alcohol are normally arranged in one particular way, head to tail, but it's possible for some of them to become reversed. And when those monomers become reversed, the polymer is more sensitive to oxidative cleavage. And it's important to know about these reversed linkages because the physical properties of your polymer may be sensitive to how many of the linkages are reversed. So we will also figure out the fraction of reversed linkages. So that's our goal. And to do this, the physical property we're going to monitor is called the viscosity. The viscosity is essentially how thick a solution is. If you think of honey, it's very viscous. For example, water's not very viscous. And hexane is less viscous yet. So we're going to measure the viscosity, and there is theoretical, some equations that will relate the viscosity to the molecular weight. One thing though, the viscosity is dependent on concentration. So to really get at the molecular weight, you have to take several measurements at different concentrations, extrapolate to zero concentration, and there you go. So we're going to make a solution of polyvinyl alcohol. We will then take part of that solution and cleave it, oxidative cleavage, with potassium periodate. And then each of those solutions, cleaved and uncleaved, we will make dilutions of. So we have two concentrations of the cleaved, two concentrations of the uncleaved, and we'll measure our viscosities. Now, we're not going to show you every detail of this experiment. The first part is simply making solutions and diluting them. You can do that. We don't need to show you. However, there are a few tricks or important details to watch out. We have to make sure we're going to weigh out our sample of polyvinyl alcohol. We have to know exactly how much we have by mass. So in the process, we cannot lose any. We'll put it into water and create the solution. We have to make sure every little bit goes into solution. And when we're done, we can't leave anything behind on a stir bar, for example. So often people will not use a stir bar, and instead will simply stir with this glass rod. If you do use a stir bar, you'll have to be very careful that you get all of the polyvinyl alcohol off of it. One thing as you do this experiment to remember is that any residue of the solution, as it evaporates, will leave a film. And one thing, you can lose some polyvinyl alcohol in that film. And secondly, as we'll see shortly, that film can clog the instrument we use to measure the viscosity. There's a small bore, as you'll see. So that's basically it. You'll use a hot plate, add a certain amount of this polyvinyl alcohol, heat it up until it all dissolves, and that will take a long time. It often takes an hour. Then you'll have to dilute it. So you'll first make a solution in this 250 ml volumetric flask. You'll take some of that out to cleave with the potassium periodate, and then each of those solutions you'll dilute into these 100 ml flasks. And those will be the 4 samples you want to analyze. Two details that I forgot to mention. One is that when you're transferring the liquid into the 100 milliliter Erlenmeyer's, you will need to use a volumetric pipette to do that. 50 mils, I believe it is. And the second thing is, after you've created your solution with the polymer, you want to examine it very carefully to see whether there are any small undissolved particles. Ideally, there will not be any, and you want to do everything you can to eliminate them. But it will take a long time to get a truly homogeneous solution without the particles. If, after all your efforts, there are still particles left, you can follow the manual suggestion and pass the solution through some glass wool to remove the particles. There is a downside if you have to do that, and that is that you can leave some of your polymer on the glass wool. You can do some rinsing, but you will lose a little bit that way, and that will give you uncertainty in the mass ultimately. But it's better to do that than leave the particles, and the reason is, I might as well show this at this point, you will ultimately be allowing your solution to pass through a very small bore. And this will be talked about shortly, and it's the length of time it takes the solution to pass through that bore that will determine the viscosity. This instrument's called a viscometer or a viscosimeter, either word does. Anyway, if you have small particles, they can get lodged in this bore, and you might not even notice it, but they'll make the timings irregular. You're short one time, fast the next, depending on what gets lodged in here. So you don't want the particulates, and that's why if you see them, you need to filter them out. Okay. So that's the introduction about how you make the samples, and now we're going to introduce you to the viscometer or viscosimeter and the process of taking your measurements of the viscosity.
Okay, this is the device which is called viscosimeter or viscosimeter, also called all-salt viscosimeter, and it is used to measure time the liquid flows between these two marks. They are called fiducial marks. This is upper fiducial mark, and this is lower fiducial mark. So, how measurements are done? 10 milliliters of water or your solution of polymer is poured in this tube, and then a rubber bulb is used to suction this liquid above the upper fiducial mark. And then this bulb is released and the liquid starts to flow down. We measure time which takes for liquid to flow from upper fiducial mark to lower fiducial mark. And the longer the time, the higher the viscosity, the shorter the time, the lower the viscosity. And that's how measurements are done. In order to maintain constant temperature, because viscosity strongly depends on temperature, we use this water bulb, and it is connected to a heater, and we have a thermometer, and during experiment we must maintain a constant temperature by adjusting this heater. Now heater is on, now heater is off, but it is important to monitor temperature, write down temperature reading maybe every 10 minutes or so, but make sure that all measurements are done at the same temperature. Another thing, it is important to, when we put our viscosimeter into water bath, it is important to that the tubes are located vertically. So now we are ready for measurements. So we will pour our solution of water here, then suction it above the upper fiducial mark and let liquid flow and take the measurements of it. So now we have 10 milliliters water inside this dosimeter, and we need to suction above the upper position. Yeah, now we are trying to suction water so that it flows above the you can see the level of water going up, coming up. Alright, yeah, you can release it now. And now you wait to start our timer. When the level of water goes through the upper division, normally for pure deionized water, this dosimeter takes about 4 to 5 minutes for liquid to flow between these two nodes. You can also watch the temperature. So it's critical that all the measurements of pure water and solutions with different concentrations of clear elements with the polymer are taken at the constant temperature. You can see now the liquid about halfway between upper mark and lower mark. About 2 minutes and 15 seconds passed since we started. So, how we control the temperature? You can see if we adjust this knob, the light goes on, it means heating continues. Heating is switched on. But if you adjust the knob, you can switch off the heating, and in such a way you can adjust the temperature. Of course, if you overheat this water bath by too much, you can bring some ice from stockroom and put some ice to reduce temperature.
Now it becomes critical to watch carefully because when the meniscus enters the bore, it descends very quickly, and you want to capture the moment at which it passes the lower fiduciary mark. Here it goes. Here it goes. Boom is when we stop the clock. Okay.
Before we do any measurements of time, and between measurements of different solutions, it's important to carefully wash the viscosimeter, rinse it with acetone to remove any parts of small particles which remain in this tube, and also dry it with air, using air relevant in the lab. So the key factors for the success of this experiment: first, maintaining constant temperature; second, keeping the viscosimeter cleaning and rinsing with acetone between every measurements. And another important thing, since when the solution is concentrated, there is higher probability to clog the pores, the tube, and in such a way upset the time measurements. Therefore, it is recommended when you have your 4 solutions ready, you do them in the order of increasing concentration and average mass. So you start with less concentrated cleaved solution, then less concentrated uncleaved solution, then concentrated cleaved, concentrated uncleaved, so that the most concentrated solution is measured last.